Welcome to the ChemDoctor, and the purpose of this presentation is to address a mega problem that usually occurs on the final exams of general chemistry courses at the university level and in the FRQ free response section of the advanced placement exam. And basically, it's the type of problem where you're asked to find the equilibrium constant of a weak acid, the percent dissociation, and the percent mass of an unknown weak acid in a mixture where the weak acid has been combined with some kind of an inert salt. So let me lay down the framework for the problem. And I'm going to do that by drawing a picture. So we're going to have basically the standard titration setup. So you're going to have a burette, all right, which my artwork is not that great, but the burette is going to, I usually represent it this way. All right, and the burette is going to hold a solution that is 0.1 molar NaOH in my example. It may be a different concentration in the course that you're taking, but that doesn't change any of the concepts that we're going to address here. All right, we're going to have a collection flask here, and in the collection flask we will take and mass out a certain amount of the weak acid mixture. All right, usually this is going to entail somewhere around a half a gram of a salt. It'll be a white salt mixture, and in the mixture you're going to have a certain proportion of that is going to be the weak acid of interest that will be cut with a certain amount of some kind of inert salt like sodium chloride might typically be used, or something else. All right, and so this half a gram will have been massed out and then dissolved in a specific volume, and the volume is pretty crucial here. In my case, I'm going to assume that we have dissolved the mixture in enough distilled water to make 50 mils of solution. All right, so I'll represent this way: 50 milliliters of solution. And you might be using a pH meter to titrate this to the equivalence point. On the other hand, you might be using an indicator. I've seen some laboratories that use 4 to 5 drops of phenolphthalein, but I've also seen labs where they've used bromethymol blue, which I'm going to abbreviate as BTB. In either case, in terms of the overall concept of a problem like this, it really doesn't matter what you're using here. If the professor or the teacher is simply interested in determining whether or not you can utilize the following lab techniques to find the equilibrium constant, the percent dissociation of the acid, and then finally the percent mass of the unknown acid that is in this mixture, this solid mixture that the acid has been combined with the inert salt. Now, before you even begin doing the titration, more than likely you will either be directed, or if this is an inquiry-based lab, the professor or the teacher is going to expect you to realize that you need the pH of the solution. All right, and so in this scenario, what I did was I took the pH of the solution after I mixed the weak acid, after I took the salt that I massed out at a half a gram and dissolved it into the 50 mils. Then I took the pH, and the pH of the solution is 3.72. Now, the reason that you need this is that hopefully you realize that once we've dissolved this mixture into the water to make the solution, you have a weak acid equilibrium that I'll show this way. So HA plus H2O, all right, and the weak acid reaches equilibrium to form H3O plus A minus. All right, and the equilibrium expression for this, which is given by the Ka, all right, is going to equal the concentration of H3O plus times the concentration of A minus divided by the concentration of HA. And the Ka is one of the things that we need here. And the pH is going to give us the concentration of H3O plus at equilibrium before any titrant has been added. All right, and the way that we get that is by taking the inverse log, so it's going to be 10 to the minus 3.72, and when we go ahead and carry that operation out on your calculator, and what I get is 1.9054 times 10 to the minus 4th molar. Now, it's important for the student to realize that we didn't just find H3O plus at equilibrium here, we also found A minus. All right, so as soon as we've taken the pH of this solution, we have found two out of the three things that we need. We've got the H3O plus and we have the A minus. That leaves the HA. Now, for percent dissociation, the student also needs to recognize, and I abbreviate my percent dissociation this way, so it's percent dis is equal to the concentration of H3O plus at equilibrium divided by the HA initial. I'll show this as HA naught times 100. So the pH has now given us the H3O plus here, and again what we need to find now is the HA because we need it for both of these subsequent calculations. I'm going to do the percent mass of the unknown acid last. So how do we find the HA? And that's where the titration comes in. So basically what you're going to do now, once we've achieved the pH of this solution, we're now going to begin dripping in the NaOH. And depending on the laboratory that you're working in, you may just take this to the end point. For the bromothymol blue, that means we're going to go to the green end point. All right. If this is phenolphthalein, which I'm going to abbreviate PT, then you're going to take this to the pink end point. All right. And if you're using a pH meter, then you're going to titrate this to a, I'll change the color of this, to a pH equal to about 8.8, where you'll terminate the titration, and this is the pH of the equivalence. I've seen all three of these methods used over the years, so you just need to equilibrate yourself, not to be redundant about terms here, to which system the teacher or the professor has you in. All right. So what we're going to go do is go ahead and titrate this, and for my example, we reach the green endpoint when we have utilized 13.1 milliliters dispensed of the NaOH solution. So how do we find the HA? Remember that this is a neutralization reaction, which is stoichiometric, so it's NaOH plus the HA, and it will give us H2O plus NaA. All right, and we have utilized a 13.1 milliliter volume of 0.1 molar solution of NaOH to get to the endpoint, which we are assuming in my example is close enough to the equivalence that the two are the same. So that means that this value here represents the moles of hydroxide, or NaOH, which is going to equal the moles of HA. And that's literally one step away from knowing the molarity of HA, which is going to give us this term right here. So let's go ahead and get the job done. We're going to have 0.0131 liters. That's just simply taking the milliliters and dividing by 1,000 to get to the volume in liters, times 0.1 mole of NaOH, which is the same as saying the OH minus. All right, and that's going to give us, oh, this is 0.1 moles of NaOH per liter. So this is going to cancel with this. So liters are out of here, and we've calculated at this point the moles of the HA. I'm going to go ahead and just switch to that right now. And what we're going to get is 0.00131 moles of HA. Now, we need the molarity of this because when we find Ka or we find percent dissociation, we have to use molarity of the original HA solution. And the one place where it's easy for the student to make a mistake here is in determining what volume to use. So let's go back to our collection flask quickly. We dissolved the HA solution, this mixture of solid weak acid that was mixed with sodium chloride, in enough water to make a 50 milliliter solution. And the HA is HA initial. We're assuming we're dealing with a weak acid here that has an equilibrium constant that is small. So we're going to be neglecting the X in this situation. So we're literally going to divide by the volume of the original HA solution before titration. And what I get here is, for my molarity, will be a molarity of 0.0262 molar of HA. All right, so now we can find the Ka of the weak acid with the information that we have. So the Ka is going to equal 1.9054 times 10 to the minus fourth, and this quantity is squared because it's going to be the molarity of the H3O plus times the molarity of the A minus. The two values are the same, so that's going to be quantity squared, and then we're going to be dividing by 0.0262 molar. All right, so my Ka for this is going to be 1.4 times 10 to the minus 6. All right, so we have that part of it done. And by the way, this value is actually not too far off from the actual Ka of this acid. But in terms of time, we need to keep moving here. So now what I'm going to do is grab the percent dissociation. I'm going to put that down here. Now, this is a weak acid, so we expect the level of ionization to be small, so we better get a small number out of this. So our H3O plus is going to be 1.9054 times 10 to the minus fourth, and that's going to be divided by my HA, which is 0.0262 times 100, and I get a value which is about 0.7% dissociated. But I'll abbreviate this way. All right, and that's in the range that we would expect for a weak acid, so that's good news. Now the last thing we need to do is find the percent mass of our HA that was in the 0.5 grams of the original solid mixture that we massed out. So to do that, I'm going to go back and I'm going to grab my value of my moles of HA, because this is the moles of HA that is in this mixture. All right, and I think what I'll do is slot it down down here. So we'll pull this value down. It's going to be 0.00131 moles of the HA. All right, and we need the molar mass here, which I see I forgot to put into this at the beginning. So it is 204.23 is the molar mass of this acid. Those of you that are with it and have really been working hard, you recognize this is actually the molar mass of KHP. So this is going to be times 204.23 grams per mole. All right, and the mass that I get is 0.267 0.75 grams of HA that was in the original sample. So my percent mass is going to be 0.2675 divided by 0.5 grams. That was what I originally massed out, was HA plus an inert salt, and then this is times 100. And the percent mass that I got was about 54%. And that basically rounds up everything that we wanted to do here in this mega problem. So we were able to calculate the Ka for the acid, we were able to get the percent dissociation of the acid, and we were able to determine the mass percentage of that acid in the original mixture where it was combined with an inert salt, which in this case might have been sodium chloride. All right, and with that I want to go ahead and close the video. I'd like to thank the viewer for coming to ChemDoctor. You can find more videos at www.chemdoctor.org.